Good morning. Today we are going to see about the following topics related to the semiconductor diode, which is drift and diffusion current, mobility of charge particle, general expression for drift current density and conductivity, drift current density of semiconductor in general, and intrinsic concentration and conductivity of the intrinsic semiconductor. So here there are two types of current in the semiconductor, that is drift current and diffusion current. There is a major difference between the drift and diffusion current. Whenever we have applied the external voltage across the semiconductor bar, there will be a random flow of the electrons which will collide with the electrons in the another atom. So that creation, that random electronic strike on atom will generate a new current which is called as the drift current. So if the drift current is purely depending upon the applied voltage, and the current which is produced due to the drifting of free electron, which is called as the drift current, and the velocity which is taken by the electron to drift is called as drift velocity. So here this is the diagram which explains the drifting of the electrons. So initially when we apply the applied voltage, all the electrons will tends to move towards the positive terminal. That's why the arrow is towards the positive terminal. So whenever it goes in straight line, there will be a collision with the atoms in electrons in the another atom, which will strike the electrons in the random way. That will create the rebounding of in a random direction, which will create the electron, which is called as the drift current. So here this is a diagram which explains the drift and diffusion current. So here the p type, from p type to n type we will have the hole diffusion, and from n type to p type we will have the electron diffusion. Here this is the region where we have the uncovered electrons, which is called as the uncovered space charge. So here in p type we have the number of electrons near to the junction, and similarly in n type number of holes near to the junction. And here so drift current, it is purely depending upon the applied electric volts. So because of the applied electric volts, there will be a random flow of the electrons which will strike the other electrons in the atoms, which will create a new current which is called as the drift current. And diffusion current, it is purely due to the non-uniform concentration of charge particles. So it is purely depending upon the carrier concentration or the concentration gradient which is occurred in the semiconductor. So whenever we have the concentration variation in the semiconductor bar, there is a tendency for the carriers to flow from high concentration area to the lower concentration area, which will produce a current which is called as the diffusion current. So diffusion is a process of the flow of charge carrier from high carrier density region to the lower carrier density region. And this is a diagram which explains a non-uniform concentration. Here in this part we have the higher concentration, whereas when it goes from left to right, the concentration degrades. So here this is a corresponding indication for the charge carriers in the high concentration part. So the each and every dot, it represents the charge carriers. Here we have the bulky charge carriers. So here there is a tendency of this huge charge carriers from this higher concentration region to the lower concentration region, which will generate a new current which is called as the diffusion current. So the diffusion current exists without the external voltage. This can be exist without the external voltage, and it is due to the concentration gradient. But while the drift current, it exists with it cannot exist without the external voltage. So the drift current will be generated when we apply the external voltage across the semiconductor bar. So what is the meaning for mobility of charge particle, right? So assume that we have the semiconductor bar, and the which bar is subjected to the external voltage. If the length of the material is L and V is the applied voltage, then you will be getting the material gets subjected to the external electric field which is applied to the E. Now we can define the mobility of the charge particle. That is a process. What is the meaning for drift? If it is the movement of electrons or the charge particles because of the electric field. So whenever we have applied the external voltage V within the semiconductor bar with the length of L, there will be existence of electric field E. Because of this electric field, there is a flow of charge carriers. That drift, that flow, it is called as a drift. So here the velocity at which the charge carriers moves, that is called as the drift velocity. So the proportionality constant. So here we have the we can represent the electric field E, that is equal to V by L. That is, it is directly proportional to the applied voltage and inversely proportional to the length of the semiconductor bar. And here you know that the velocity of the charge carrier is directly proportional to the electric field. And in order to cancel this proportionality constant, we have introduced this one constant that is called as the mu here. That mu, it is represented as mobility here. So mu is the mobility of charge carrier, it is just given by the ratio of the applied external voltage divided by the electric field which is generated by the applied voltage. So mu is generally it is used to represent mobility, and if it is with respect to free electron, that is represented by mu n, and if it is for hole, it is represented by mu p. Then what is the meaning for general expression for drift current density and conductivity? So here in this diagram we have the tube of semiconductor which is of length L and the area of cross section of A, and we have applied the external voltage V across this semiconductor tube with the positive and negative terminal here. So here what is the process here? Here when we apply the supply voltage, all the electrons will tends to move towards this positive terminal. That's why the arrow is here. So area A is the area of cross section and L is the length of the bar and V is the applied voltage. And here time, capital T, it is a time taken by electrons to travel a distance L. So we have defined the velocity V, that is called as the drift velocity, which is given by the ratio L by D. So we know already the electric field which is equal to V by L. So by having all these things, so N is the number of electrons passing through the total area in total time T. So the number of electrons in the total area, that is given with the ratio N by D. You know already what is Q, that is equal to charge of free electrons, which is equal to 1.6 into 10 power minus 19. So if you want to calculate the total charge in the total area A, that is equal to dQ is equal to N by T. So you know already N by T, it is a total electrons in the total electron which passes the area of cross section A at time T. So if you multiply that by charge, you will be getting the total charge. So the total charge is equal to NQ by T. Now we want to calculate the total current, that is equal to charge in unit time divided by unit time. So NQ by T divided by 1 second, that is equal to NQ by T. So now we can able to, by using this current equation, you can able to calculate the current density which is given by this expression J is equal to I by A, that is equal to, so we know already what is I, that is equal to NQ by T. So now we have divided that expression by A, you will be getting NQ by AT. But you know the equation for T, that is equal to given by this previous expression, that is V is equal to L by T here. So if you use that expression here, L is equal to T is equal to L by V. So if I replace this T by L by V, you will be getting this new expression for current density. But here in this, the denominator LA, it is the length into area, that is equal to volume, we know that. So which is called as, so if we substitute N divided by LA, if you take this alone, N by LA, it is equal to number of electrons per meter cube. That is, meter cube means it represents the per volume. So that is called as the concentration of free electrons. So that is represented by J, that is equal to NQ into V, where N is the N by L, that is N is the concentration of charge carrier. So general expression for current density, J is equal to NQ mu E area per meter square, ampere per meter square. The current density is related to the electric field in general by using the Ohm's law. With this equation, J is equal to sigma into E. So now we have two equations for current density. One is this one and the another one is this one. So if I equate these two, you will be getting this expression. If I equate, and you will be getting the cancellation of E on both sides. So the remaining is sigma is equal to NQ by mu. That is called as the conductivity. And we have the general expression for resistivity. Rho is the resistivity, which is the reciprocal of conductivity. So if I substitute the conductivity equation from this here, you will be getting the equation for resistivity, that is equal to 1 by NQ mu. Right? Thank you.